In section 2, we're going to be taking a look at Rolle's theorem and the mean value theorem. And Rolle's theorem is really just a special case of the mean value theorem. So consider this situation over here. We have a boat that starts out here at P, ends up here at Q. I suppose you could go on a straight line to get there, but the boat, being a sailboat, goes in a zigzag or curvy line. So is there any way to be able to go from P to Q without ever sailing in the exact same direction? So the same direction would be the slope of the straight line path. Well, there would be a situation right here where our slope of our tangent line is the exact same as the slope of our original straight line distance. And there'd be a second one up here. So in this case, there would be two spots where the slope between our 2 points was equal to our derivative. So no matter how we did this, we could even just curve down here and then curve back up. Well, I suppose I could even draw that in. Even if I curved down and then curved up, at some point, I would then have a spot right here where my derivative, the slope of my instantaneous rate of change, would be equal to the slope in between 2 points. There's many ways you could go from P to Q, but at some point there has to be at least one spot along that curve that has the same slope. And that's really what the mean value theorem is saying. And when we say mean, we're not talking about not meaning not nice. Mean in mathematics means average. For the most part, the slope between any 2 points where you start and end has to be equal to your derivative at some point in between A and B, the endpoints. But that's assuming that you have a continuous interval and that it's differentiable on that whole interval. Now the mean value theorem down here says suppose that your function is continuous on a closed interval and differentiable on the open interval, because your derivatives don't exist at a point on the ends. That's why it's an open. Then we would get this here where C is somewhere in between A and B. And you might be wondering, like, where the heck does this come from? Well, all we have to do is take this right here, bring it down. Notice right here it's f of b minus f of a. All they're doing is just taking this bottom part, multiplying both sides by this bottom part, which puts it over here with your derivative. And that's what we have right here. So it's really this thing here where your slope between 2 points, the right-hand side, is equal to your derivative at some point between A and B. So here we need to go ahead and take a look at this. First of all, can we actually apply the mean value theorem to this function? Well, it has to be a continuous function. We would know because we're dividing by x, what would cause the bottom to be 0, in this case would be 0. But that's not an issue because we're on the closed interval from 1 to 3, and 0 is not in that interval. So it would be continuous. The question is, well, does your derivative exist? Well, let's go ahead and take a look at your original function and simplify it a little bit, and then we'll go ahead and look at your derivative. If you distribute this, basically dividing by x is multiplying by x to the negative 1. Distribute that through, x times x to the negative 1 is 1. X to the negative 1 times your 1 is this. If we take our derivative, this goes to 0. This exponent in front, decrease it by 1, we would get this. So in other words, we get our derivative to be this, or just negative 1 over x squared. Now, we would know we would have issues with our derivative whenever the bottom of our derivative is 0, which in this case is 0. But that's not an issue because 0 is not in your closed interval. So it is continuous, it is differentiable. So our derivative must be equal to our slope. Well, let's go ahead and find our slope. This is your x being 1. Take 1 and plug it in here, and we would get an output of 2. This is your x being 3. Take 3, plug it in, and we would get an output of 4/3. So now we can go and subtract the two y values, and then subtract our two x values, 3 minus 1. And then simplify. So on top we would get negative 2/3. On the bottom we get 2. Negative 2/3 divided by negative 2 is negative 1/3. So the mean value theorem states that your derivative, which we have here in orange, has to be equal to your slope between your 2 points, which we have here in purple. So now all we'd have to do is go ahead and solve this. You could multiply both sides. It's a fraction equaling a fraction, so I suppose you could cross multiply, or you could just go ahead and multiply both sides by your least common denominator. But if you, either way, it doesn't make a difference. You get to this point where x squared is equal to 3. And then you take your square root of both sides to be able to get x. Now, our answer is only the positive root. Because remember, our closed interval was from 1 to 3. And the positive square root of 3 is in that interval. The negative square root of 3 is not in that interval, so we would not use it. So, looking at our problem here, when is the slope between these 2 points, which is negative 1/3, equal to our derivative when at x is equal to the square root of 3. Now, Rolle's theorem is just a special case of the mean value theorem. The mean value theorem basically says these 2 points that you have, you're just finding the slope in between them. They can be at any height, and you can still find your slope. Rolle's theorem basically says your 2 points need to be at the same height. You plug in A, you plug in B, you get out the same height. So that's what it's saying. That's the main difference. So it still has to be continuous on a closed interval, differentiable on an open interval, but you have one additional thing where your two endpoints, when you plug in A and plug in B, you get the same output. Then there's some number in between where your slope is equal to your derivative. Yeah, remember, if you start out here and go straight over here, you're not going up, you're not going down. The change in your y would be 0. 0 divided by anything is 0. So that's why your slope is 0 whenever you're looking at Rolle's theorem. And so your slope is equal to your derivative, just like the mean value theorem says. But remember, Rolle's theorem, your two endpoints have to be at the same height, so that's why it's 0 there. So here, let's go ahead and find our two zeros, because that would mean when x is 0, and you plug in another x here, you get out 0, so they'd be at the same height. So all we'd have to do is set this equal to 0 and solve it. So we could factor out our smaller of the two exponents, we get this. Now we'd have two things multiplied together to give you 0. You set the first thing equal to 0, then you could square both sides and you get 0. Set the second thing equal to 0, and you solve that and you get 1. So Rolle's theorem, it needs to be continuous, so you can draw this without ever lifting up your pencil. We don't have to be concerned about our interval being 0 to 1. We don't have to be concerned about having negatives and roots, because our 2 points where it's at the same height, they're at 0 and 1. They're not negative. And it would have to be differentiable. Well, we'd have to go ahead and do our derivative. So exponent in front, decrease it by 1. Exponent in front, decrease it by 1. So now we want to go ahead, and I'm going to pull out the over 2, which would basically be pulling out the 1/2. And I'm going to pull out the smaller of the two exponents, which would be x to the negative 1/2. And then you look at what's left. Well, I just pulled out this whole thing here, so I have a 1 minus, I pulled out the over 2, so it would leave me with a 3, and then just an x to the first. Because remember, if you would distribute this through, x to the power times x to the power. You'd have to add these exponents. So negative 1/2 plus what exponent here would be 1/2, and that's an exponent of 1. So in front here, this negative exponent would go down. The 1/2 would cause a 2 to be in the bottom. So this would be our derivative. So then you'd have to think, okay, is it differentiable on our interval of 0 to 1? Well, it's going to have issues whenever the bottom is 0, which is 0. So we're going to have issues at 0, but remember, Rolle's theorem in mean value says it has to be continuous on a closed interval, differentiable on the open interval. We had issues at 0, but that's the open interval part here, so we're okay with that. So Rolle's theorem can be applied because we have a closed interval, 0 to 1, continuous function, and it's differentiable. So that means we have to take our derivative, set it equal to 0 then for Rolle's theorem. You set your derivative equal to 0. The only way this is going to be 0 is when the top is 0. 0 divided by anything is 0. So you set the top equal to 0, you solve it, and you get 1/3. 1/3 is in between 1 and 0. So that does work. So at x being 1/3 right here, we would have 0, which would be a horizontal tangent for your slope, which would be the same as going from here to here with your slope. So what's the use of mean value or Rolle's theorem? Well, consider this situation here. Suppose you're driving on a toll road. At some point, your average velocity has to be equal to your instantaneous velocity. So consider two toll booths that are 70 miles apart. And you drive from the first toll booth to the second one in exactly 1 hour. So at some point, you were driving 70 miles an hour. But if the posted speed is 65, the Pennsylvania police will say, oh, at some point you were speeding, therefore we give you a ticket. And they don't even have to see you. And it's not just Pennsylvania that does that. Indiana is also the exact same way. So some toll booths are a certain distance apart, like going around Chicago, where they don't really care how fast you go from one to the other. But once you cross the border from Illinois into Indiana, all of a sudden, nobody's speeding. Why aren't they speeding? Because of the mean value theorem.